All right, welcome back to the next video in this series, where in the previous video, we motivated why pure calculus may not always be the best approach to trying to solve these various integrals and differential equations. And as promised, this video is here to introduce an easier way to do that. So we're going to work with the same differential equation as the previous video, which is derived from the ball of mass m free falling, and it's affected by the forces of gravity and some damping force. And we said that rather than having just a second order differential equation, the true base equation of motion for this system was first order. There's going to be a whole video on that when we're getting to modeling. For now, just kind of take that as truth, given that we're more focused on solving the equation than deriving the equation. So our equation, after applying Newton's laws with sum of forces in the x direction positive down by our definition, we got it was mv dot equals mg minus bv. So anytime we have a differential equation, and again, this is our equation of motion, we are trying to solve it, figure out what the motion's going to be, what is the solution in time looking like. And we're going to have inputs and outputs. In this case, we're going to have like our variable of interest. Our output of the system is velocity. So we're going to want to group everything that's a function of the variable we're interested in on the left-hand side of the equation. So we'll rewrite this as mv dot plus bv is equal to mg. This is the standard way of writing that differential equation. Our input, our force acting on the system, is gravity, so that's on the right-hand side, and everything that's a function of the variable we're interested in is on the left-hand side. It's very important for this setup because, as we had mentioned at the end of the last video, there's two parts to the solution we're really interested in finding. The first is the free response of the system. So what happens when no inputs applied? It's purely a function of the initial conditions. The other thing we're interested in is the forced response. And that is a function of the forcing function. I just said function a lot, but such as life. I'll say function of the input. So the way that we can do this is we're going to analyze the homogeneous response. And we're going to look at the particular, we're going to get the homogeneous solution and then the particular solution. And we'll add those together to get the full solution to the differential equation. So the way that we denote this is the homogeneous solution I'll just call y sub h of t, and the particular solution will be y sub p of t. And then the full solution, y of t is the homogeneous solution plus the particular solution. Okay, so let's put this into practice real quick. Let's get the homogeneous response to the system. Well, for a differential equation to be homogeneous, there needs to be no input. The right-hand side of the equation needs to be set equal to 0. Again, it's assuming that no input is applied. So, just for this part, we're setting mg equal to 0, we want to know what is the solution to the differential equation mv dot plus bv is equal to 0. What is the solution to that differential equation? That's the homogeneous part. Homogeneous meaning no input on the right side of the equation. We've set it all to 0. So assuming constant coefficients here, we're going to say that the solution to the differential equation v of t, if I use this, v of t is going to be equal to some constant a times e raised to the st, and the derivative v dot of t is going to be a times s e raised to the st. So we can plug these back into our homogeneous equation, and we get m times a s e raised to the st plus b times a e to the st is equal to 0. We can pull an a e to the st out of this, and we're left with ms plus b times a e to the st is equal to 0. So there's two ways that this equation could be solved. There is a trivial solution where a is equal to 0, and that would solve this equation. But we're not interested in the trivial solution. We're going to look at what happens when s is equal to minus b over m. So using s is equal to b over m, our homogeneous solution, I should actually say it's v here. I know I used y earlier, but now we're solving specifically for v. The homogeneous solution is going to be a e to the minus b over m times t. Great. We'll solve for a given that we have an initial condition. An initial condition is going to be required to solve for that coefficient. For the particular solution, what we're going to use is the method of undetermined coefficients, which says, given that you know the form of the input, that you can figure out, like you can guess the solution of the form of the particular solution. So I kind of stumbled over those words a little bit, but what exactly does that mean? So coming back, right, we're done with the homogeneous solution. We're considering the input again. So now we're on to the particular solution. And our equation was mv dot plus bv equals mg. Well, m and g are both constants here, so our input is a constant. And that method of undetermined coefficients says that if we have some constant input, that the particular solution is going to be a constant. So the particular solution is going to be some constant, I'll call it c, and then the derivative of that particular solution, given that it's a constant, is now 0. So m times 0 is going to be 0. We're left with b times our constant is equal to mg. We can now directly solve for c, and we get that c is equal to mg over b. So now we have that the particular solution is equal to mg over b. Now the time has come that we need to combine our homogeneous and particular solutions, because we've solved for the homogeneous form, we've solved for the particular. We need to combine those two. And again, this is kind of akin to the free and forced response. This would be kind of our forced response. You know, what's the system doing as a function of the input? And up here, this is our free response, because it's just dependent, it's going to be dependent on our initial condition to solve for that coefficient a. So, full solution time. Given that we had mv dot plus bv equals mg, and now I'm going to say that our initial condition is that at time equals 0, our velocity was 0, so we're starting from rest. We have v of t is equal to ae to the minus b over m t plus mg over b. And given that at time equals 0, velocity is equal to 0, we have 0 equals a e to the minus b over m times 0 plus mg over b. E raised to the 0 is 1, so that's now just 1. We can move mg over b over, and we get that a is equal to minus mg over b. Great. Given our one initial condition, we solved for that one unknown coefficient, so that now gives us our full solution. V of t is equal to m minus mg over b times e raised to the b over m times t plus mg over b. And that is a far simpler way for us to solve that first order differential equation that we had in the previous example. You can verify that yourself if you want to go back to the prior video and plug in what happens when v of 0 equals 0. And plug in that t0 is 0 yourself, and it'll simplify down to this equation if you really want to check for yourself. But that is it for solving just a plain first order differential equation. There's going to be plenty of this in the rest of the video series. The next video will cover solving the second order differential equation.